I'm Schmidt with Cox Colvin and Associates. We're an environmental consulting firm in Central Ohio of about 20 people. And we do the usual groundwater, soil, etc. But we've done a lot of soil gas prospecting for VOC sources and vapor intrusion, especially in recent years because of the development of the vapor pit. And I'm going to talk about a little bit about soil gas sampling techniques and how they affect sample quality, and I'll bring it back around to spatial heterogeneity at the end. So, let's see. One common way of collecting soil gas samples is with direct push, commonly called geoprobe. This is a rig that's putting in temporary sample points using post-run tubing. You run the tubing down there, let it sit for half an hour, collect your sample. Good, cheap way to collect data you can't resample very well. If you do want to resample, then you probably want to do something like this, a soil gas implant where you've got a small screen surrounded by a sand pack, separated by bentonite, etc., as in this figure in the back of the Hawaii guidance. And you can go back and do repeat sampling here. Somewhat higher data quality typically. You can do more or less the same thing in a limited space. This figure on the right is from the California guidance, and they recommend, at least one way they recommend of collecting sub-slab soil gas from a very shallow depth immediately beneath the floor, is the same kind of arrangement with a screen and a sand pack and everything constructed in a limited space of about a foot vertically. You can do that. You can get good data from this or from the earlier ones, but this is a rather costly, time-consuming process of typically coring a hole through the concrete first, etc. None of the equipment is very usable. More common approach for shallow sub-slab soil gas, that is through a floor, typically inside a building, is shown in this figure from the Raymark investigation by EPA's Dom DiGiulio. And this figure shows up in a lot of the guidance. And basically he drilled a hole through a slab and put hardware, brass, stainless steel, swage lock, etc., with compression fittings usually, in the slab, and then collect vapors through the slab and into your sample container, canister, sumacan, what have you. This requires cementing around the probe and between the probe and the concrete, and it does have some limitations. You can see that the cement going around there is a relatively small area. They have a tendency to break loose, including to the author here, and to probably about everybody who's tried this. You have to wait for the cement to get set up and typically come back and sample on the next day. You normally would not be able to reuse this hardware. You can get good data from it, but again, there's limitations, for which reason we came up with a vapor pen, and I won't talk about this a huge amount. It's in the back of the Hawaii guidance. You can see pictures and SOPs. But the advantage of this is that the vapor pen is held in with a silicone sleeve, so there's no cement to set up. You don't have to worry about getting a complete seal around it. It's got a threaded section on top that you can screw a lid down onto, and you can pull it up when you're done sampling, and a barbed connection instead of compression fitting. Installation is simple. You drill a 5/8 inch hole, dust it out, hammer it in. We've put in as many as 90 of these things in a day, just 2 guys and a hammer drill. So they definitely go quick. On the left, I've got a stick-up configuration. This is if you don't mind having 3/4 of an inch of hardware sticking up above grade. So you put a traffic cone on it, come back and sample later in the day, pull it out and plug it when you're done. If you're going to leave it there for repeat sampling, that would be more typical of vapor intrusion. The stick-up is more common if you're looking for sources, and once you find your VOCs, you pull them out and leave. If you're going to do repeat sampling, you drill an 1.5 inch hole and then a 5/8 inch hole through that, hammer the whole thing below grade, and you can screw this cover on the top of it, run over it with a forklift, walk over it, whatever you want. So much for different sample devices. There's a lot of discussion in the literature versus concerning purging. You've got to get that clean air out of the sample tubing and the sand if you have a sand pack, etc. And you want to get good dirty soil gas in there. So here I'm purging with a multi-gas meter, the yellow device. And well, you can use a couple of things. You can use a syringe and just pull it out until you get the right amount of soil gas. You can use a peristaltic pump, although you don't want to use that for the actual sampling. I'm using a PID. And the advantage is this PID and multi-gas meter, I can read my Oxygen, I can see LEL if I have explosive gases, typical in a hydrocarbon situation, carbon dioxide, depending upon the meter. You can see there I've also got a vacuum gauge. That little dial gauge is telling me if it's tight soil. I'm drawing vapors at 200 milliliters a minute, and if I get an indication of vacuum, then I have tight soil. It might preclude sampling, and that'll be useful information later on if I decide I need to mitigate. There are many discussions too on purge volumes. A lot of the guidance, including Hawaii, uses a default of 3 purge volumes before you have good soil gas in your tubing. But you can also, what I like to do and what the Hawaii guidance allows, is to watch your meters. And you can see that the oxygen here, when I start purging, the oxygen drops. I always see that. PID, if you have VOCs, the PID rises. And at the end of the purge period, depending upon your hardware, with a vapor pin, it's typically about 20 seconds. When things level off, then you're ready to sample. Containers, different sample containers will give you different results, and they have their pros and cons as well. If I'm looking for sources, I'll often use these. These are little 22 mil evacuated vials, a little smaller than a VOA bottle for groundwater. They're cheap. They don't have the lowest reporting level. They use straight GC, so we can get down to about 10 parts per billion. That's great for finding sources, may or may not be low enough for vapor intrusion purposes. But I inject my syringe down into the tubing, directly into that's a vapor pin there, stick up. Pull out the soil gas and inject it into the end of that vial, send it off to the lab. Obviously very compact. A lot of people like Tedlar bags. They're cheap and you can throw them away when you're done, so there's no risk of cross-contamination, but they do have limited holding times, typically 2 days, and they have potential interferences, which is to say they contribute some VOCs and take away others. I've used them to transfer gases sometimes, and I might measure field parameters out of them, but I'm not a fan myself, but they're certainly usable too. Bottle vacs, these are made by the same guys who came up with the Encore sampler for soil sampling. And these are disposed of in between at the end of sampling, so you don't have to worry about cross-contamination. They're a simple device. You cannot take an 8 or a 24-hour sample with them. It's just a 200 milliliter per minute grab sample, but you can get good data out of these. Reporting levels are fairly close to Sumicans, and they come in various sizes, so bulk is not quite the issue that it would be with a Sumican. Of course, Sumicans, presumably you're familiar with. These are regarded as a gold standard for sampling. Again, they'll give good data, but there are issues with the regulators. I found most labs, the limitation is, we've had 1 or 2 really poor labs, and the limitation was not, I don't think, in the analysis, but in the equipment. These can clog, they can leak, sometimes both. So it's very important that you test them before sampling and always have a spare with you. But you can obviously get good data with these. Active soil gas, and just so that it's clear, active sorbents, just so that it's clear, Harry in the second half is going to talk about passive sorbents, where you put one in place and it basically soaks up vapors. An active sorbent, that's the tube here in the upper right, it's about half the length of a pencil, and you can pull vapors through that using a syringe or other devices. I show a pump on the left. It'll pull a known amount of air through that sample, through that sorbent, and that'll be your sample. So a passive sorbent, you don't know how much air it represents. They're compact. They're good for a lot of compounds, including some heavier things and some of the lighter SVOCs, which a Suma canister wouldn't sample. But it's fairly critical. You have to have some idea what you're sampling, what the concentration is, et cetera. You have to pull at the right rate, or you'll get a lousy sample. So you have to have a fair amount of expertise and knowledge before you go in using one of these. I'll talk now briefly about tubing. Just in general, soft tubing shown on the left will give you more interference. It absorbs more VOCs and gives off others. Stainless steel on the far right is the least reactive tubing, but not practical for a lot of field applications. So most people use nylon or Teflon or PEEK over there toward the right. I personally like nylon. Now there are a lot of studies, including Greg Ouellette has often shown, you often see a figure of his. It's a graph where he sent hydrocarbons through 50 feet of tubing. And when the hydrocarbons got to the end of the 50 feet of the Tygon tubing, for example, there wasn't much left. He lost about 90% of his compounds. Teflon showed up as best, nylon fairly close. Various studies, some show one is better, one is the other, but they all agree that the soft tubing is relatively bad. But it's important to keep in mind the context in which you're using it. We use Tygon on the vapor pins to make connections. We don't use it for long length, certainly not 50 feet, but we'll use maybe a ½ an inch of Tygon or less to connect our Nylaflow to the vapor pin. The barb fitting where you saw the vacuum gauge that was held with Tygon tubing. I've got soil gas only in contact with maybe 5 or 6 millimeters of tubing, not 50 feet. So it's very important when you use a softer tubing, you can do that and you can get valid samples, but don't use any more than you have to. I'll show you a couple of slides here where we did comparisons of the vapor pin to other devices that did not use any soft tubing. You can see the same results. This is an investigation we did with Matt Williams of the Michigan DEQ. We had 4 vapor pins next to 4 Swagelok stainless steel hardware sampling devices, subslab devices set in cement. And you can see the Swagelok data on the horizontal axis, vapor pin data on the vertical axis. You get the same results. And it doesn't matter if you're looking at low or high concentrations, there's no addition, no contribution, or no subtraction from that little bit of soft tubing. A similar study was done by Susie Nowickas of H&P Mobile Labs. This is the one founded by Hartman, sorry. Yeah, but at any rate, but this is a big lab in the vapor intrusion world. You're probably familiar with it. What Susie did here, she had 10 vapor pins next to 10 of the California scheme, where she had stainless steel screens set in cement slabs with a sand pack, etc. And again, you get the same results. It's obvious that there's no contribution or loss from that little bit of soft tubing. So you can use a little bit of soft tubing, use it properly, don't use any 50 feet. Leak detection is another issue people discuss at great length. This is a scheme proposed by Dom DiGiulio, the guy who had that earlier figure showing a type of subslab device, and he tended to have some leaks with his equipment, so he proposed this where you surround your sampling hardware, and especially the point going through the slab, you surround it with helium. Some people use VOCs like isopropyl, and if you have helium or isopropyl in your sample, he's getting real-time readings with the device there on the left side, then you realize you have to fix it, you tighten up, et cetera, till you have no leaks. You can do that, but you're not going to do very many of them in a day. It's obviously cumbersome, it's costly, it's difficult to carry, you can't carry the helium on an airplane, et cetera. So I like a simple vacuum test. And again, this is approved in the Hawaii guidance. And Susie Nowickas commented here last year that shut-in test is the most effective way to identify and prevent surface leaks. I agree completely. This is obviously not a real sampling device on the left, but just to show the concept that barbed fittings work great if you have the right size fittings. I have more than 20 connections here. I put a vacuum on it with a hand pump, and 5 minutes later, my vacuum gauge shows the same pressure. I didn't have a leak. As to the point going through the slab, you surround it with water. There's a stick-up point on the right. I just surround it with distilled water using a piece of PVC pipe and some Play-Doh. If I have a flush mount, then I can pour the water directly into the 1.5-inch hole. If you don't lose the water, it didn't leak. And if you have good hardware, you won't see any leaks. I've never had one using this device. All right, I'm going to bring it around a little more now to sample spatial heterogeneity in soil gas. This is a case study from a site that we investigated in Western Ohio. And this is, well, it's typical of a lot of sites. We had several suspect sources. We had PCE and TCE decreasing, a couple of defunct degreasers, a couple of above ground storage tanks, and we had groundwater contamination coming from under the building. But we had not investigated in the building, and it was a little unusual because for various reasons, the client told us, I'd like to know if we have any contamination under the building, and I'd like to know it in the next few weeks. And you know how it is, you can collect soil samples, send them to the lab, get back your results Reiterative processes can take months or years. But we had just developed a vapor pen, and we said, well, we think we can do this in a few weeks, and our approach was to collect subslab soil gas points in a 20-foot spacing, collect samples from them, send them to the lab. And this is what we saw. Using the field instrument, just 2 guys and a hammer drill, we'd put in about 30 points a night, screen them, sample them, pull the points and plug them, and then do another 30 the next night. We did 144 in a week. And we found high levels of soil gas where you've got the big black circles on a logarithmic scale. So those are pretty high levels. And they don't look anything like where we thought the contamination ought to be. That's kind of curious. We followed up with those small glass vials I showed early on and sent them to the lab. What we do now is we would normally send only the hot ones on the basis of the field PID. We'd send only a select number of samples to the lab instead of having to analyze all of them. But at that time, we were paying $100 a piece for the little glass vials. And we get the same kind of data, except we can see which compound is what. Blue is one compound, red is another. We followed up with soil sampling, but it has the advantage we sampled only now over a relatively small part of the plant instead of having to carry a geoprobe and core big holes through the floor everywhere in the building. And the soil contamination looked pretty much exactly like the soil gas contamination. I'll mention too here that the soil is contaminated at a depth of about 15 feet. Your contamination doesn't have to be right under the floor. So how did it get that way? Why is the contamination not where we thought it would be, where the magenta rectangles are? When we look at site history using Sanborn maps and aerial photos, you can see the buildings in 1924. In 1933, the previous owner had purchased a house, started building stuff in his garage, maybe using solvents, we don't know just when. By 1938, his building, though, had expanded to look like this gray T-shaped thing. Another couple of expansions, but by 1950, the building looked like this. Now you notice that your contamination, this is of course the grease and soil contamination, looks a lot like the location of loading docks and back doors. By 1950, the building had expanded to look like this. That blue contamination, the PCE contamination, especially on the left, must have happened before 1952. Now think about this, when you do a facility investigation, you always look for the old guy to ask him questions. There's nobody around who's going to remember what happened in 1952. So you just have to collect a lot of samples to get this kind of information. The building had expanded to its current configuration in '66 and looks like this. So the implications now for vapor intrusion. This is a graph I pulled out of EPA's vapor intrusion database in 2012, where they compared attenuation factors for soil gas, subslab and exterior, and groundwater. And this is a graph showing the empirical databases similar to the one that some of the stuff that Roger showed early on. They collected indoor air, they collected subsurface data, and they compared them. What is that empirical attenuation factor? If you look at the subslab on the right, I've heard people say, well, subslab is no good because subslab is a poor predictor of indoor air. It's true, it's a blunt instrument. There's quite a bit of slop. If you look at their plot, if you look in between the 5th and the 95th percentile of attenuation factors, there's a factor of 81 variation. So if you use your subslab data out of EPA's database to predict indoor air, you can get a different answer by a factor of 81, depending upon where we were looking. Groundwater, though, is more variable. The variability in the attenuation factors between the 5th and 95th percentile is a factor of 330. Exterior soil gas is a variability of a factor of 3,300. It's 40 times sloppier than subslab soil gas. So subslab may be a blunt instrument, but it's the best thing we've got before going into indoor air. Just to compare temporal and spatial variability, I don't have time to go into these radar plots. I've given a couple presentations and I can send you information if you'd like on this. But this is a device, a method I came up with to compare subslab and various kinds of soil gas very quickly. And just focus for now on the polygon shape. The concentrations are lowest in the middle, they're highest on the outside on a logarithmic scale. You can see the indoor air, which are the blue polygons on the left. are fairly variable. Now I'm showing in this slide temporal variability. So I'm showing indoor air on the left, subslab soil gas on the right. And you can see that my variability, one location on different dates, my variability is much greater in indoor air. I have about an order of magnitude difference there. Whereas my subslab soil gas, my variability is very low. My PC, TC, DC varied over a year by no more than a factor of 3. And that's consistent with what Tom McHugh and various others have seen in soil gas. Spatial variability is another story. From the same facility on the left, you can see now my polygons for indoor air. These are taken at multiple locations, but on a single date. So that spatial variability in indoor air within this building, at least, is very slight. Those polygons on the left are all the same shape. The polygons on the right for subslab soil gas are extremely variable. You get a lot of variation over just 20 feet or less. So your biggest problem: tubing type, purge volume and rate, sample type and container, or your leak detection method. I hope you said none of the above. It's spatial heterogeneity. Going back to my earlier case study, if you look at the heterogeneity now in this building, even just looking between the first and the third quartile, just my central, half of those 144 points, my PCE concentrations vary by more than 2 orders of magnitude. And so you have to either collect a lot of samples to get around a building like this, or any kind of soil gas is variable enough. You have to collect a lot of data, or you have to collect larger data. You have to collect samples representing larger areas. So with that, are there any questions? I don't know, did you want to take questions at the end or take them now? I can go either way.
Hey, Mort. Yeah,
I'll turn it over.
You can take any questions we have now. So if anyone has questions, yeah, there's a Q&A option. You can just input them. Haven't seen any to the moment, but then Roger had some comments. Okay, let's save those for the end. So if anyone has anything, we'll take questions for the next minute or two, and then
you can go ahead to Harry.
Yeah, and we're gonna have Harry coming up, ready to go soon. So
let's go ahead straight to Harry.
Yeah. So hey, Harry, when you're ready.
Okay. Let me share screen. Okay. Can you see my screen now?
Yes, we can. It looks good.
Okay. All right, great. Well, Roger and Jordan, thank you. And I want to thank everyone for attending their talk today, which my talk is going to be on the use of passive soil gas sampling to collect high resolution, time integrated data to support site characterization and vapor intrusion investigations. As Mort's talk showed, spatial variability and subsurface contamination is the norm. And too many sites are being inadequately characterized by following poke and hope sampling strategies or allowing site access and manager bias to dictate where samples are collected. A sampling plan that collects high resolution data will better define contamination and create a better conceptual site model. But what is high resolution? I know we have a few people here from international locations, but for those of you who watch American sports, you've probably seen this commercial where the announcer asks, what is better, more or less? And the premise goes that even a child knows that more is better. And what we have found from conducting site investigations for over 20 years is that this applies to characterizing sites because of the spatial variability and subsurface conditions. So what sample spacing is reasonable to collect high resolution data? This slide shows the results of a passive soil gas survey with a grid that has 90 feet between sample locations. And as you can see, there are definite areas of higher measurements, suggesting the presence of source areas in a few locations. However, what if a tighter grid spacing was used, such as what was actually done, with 30 feet between sample locations? Here you see there are areas of contamination that were completely missed with a 90-foot grid, and even those areas where contamination was identified are much better defined with a 30-foot grid to reflect where the true hotspots are located. So more is better as long as quality data is collected, which I'll discuss shortly. I'd like to get you thinking about how a passive soil gas survey can answer the question, where for your projects? Where is contamination? Where should I collect soil and groundwater samples? Where is vapor intrusion risk? Where is the center of massive contamination at my site so I can focus my remediation and reduce the overall project cost? A passive soil gas technology is routinely used to answer these questions and guide project decisions. As Mort discussed and the prior slide showed, spatial variability is the norm at sites, and sampling for compounds and soil gas allows you to overcome that challenge by collecting more data because of the lower costs associated with collecting the samples as well as analyses. Plus, a time-integrated passive sampler is absorbing compounds over days or weeks, and if there is contamination in soil or groundwater in close proximity, the soil gas will be contaminated, which will be absorbed by the passive sampler. With soil or groundwater sampling, you need to sample at the exact location and depth to identify whether contamination is present. Therefore, the broader area of influence of a passive soil gas sampler allows for a PSG survey to be less likely to miss contamination by reducing data gaps between locations. A passive soil gas survey also overcomes the challenges from the temporal variability in soil gas concentrations by collecting time-integrated samples over several days or weeks. Now, Mort showed where there was really high concentrations, there wasn't much variability, but what we've seen is that there is temporal variability with lower soil gas concentrations, and that's been supported also by what Dr. Paul Johnson saw out at the Sun Devil Manor House out in Utah. As the table notes, not only were 2 orders of magnitude variability identified spatially, but an order of magnitude variability was seen temporally. And this is in agreement with what we've seen also at sites, and in fact, it is common to have significant diurnal swings in soil gas concentrations, particularly when no concrete or asphalt covering is present. Now, Beacon's technology is provided through use of soil gas sample collection kits, which we ship out to our clients for them to collect the samples themselves. They're shipped out in a rugged toolbox. It's approximately 20 inches by 10 inches by 10 inches. And it's shipped out with a tug-tight custody seal on to make sure that nothing's tampered with during delivery. Each kit is custom packaged with the appropriate number of samplers, depending on the size of the investigation, whether it be 10, 20, 50, or 100. And no ice or preservatives are required for shipment, which makes it a lot easier to ship these not only throughout the United States, but internationally, and you don't have to worry about short duration for shipment times, because the hold time on using sorbent samplers is 30 days. And the kits include detailed instructions, and there's also installation videos that can be found on our website. This is what our sampler looks like. There's various ones out there, but ours is about the size of your pinky, and it contains 2 types of adsorbents. So we can target from vinyl chloride out to the lighter pHs with one analysis. There's 2 pairs of adsorbents in there, so we can have a duplicate analysis for every location, or also have confirmatory analysis if anything doesn't look right with our QC checks. Each sampler has a uniform massive adsorbent present, which is verified with an analytical balance, which is important because what we're looking at is relative differences from one location to another. So you want to have everything in control as much as possible with your sampler and the analyses, because what's out of control is the variability in your subsurface. Our sampler is also completely inert. If you notice, there's coloration to the sorbent traps that's inside that vial, because we put the stainless steel meshing frames through the same passivation process that's done for the inside of suma canisters before we put adsorbent in there. So the sampler is completely inert, which is in accordance with the ASTM requirements. We ship it out with a solid cap on it, which is white there, that's shown on top. When you're ready to install it, you just remove that solid cap, put a sampling cap on there that has a hole through the center, covered by screen meshing to allow gases to freely come into the vial, extend that retrieval wire out from it, and lower it down into the hole. Simple process. All right, there's various adsorbents that are used for targeting organic compounds, whether it be in soil gas or air. And you can have carbon molecular sieves, blacks, polymers, and they all differ in their composition, as well as their surface area and their hydrophobic properties, and their ability to absorb and then release compounds. And so it's important to know what compounds you're targeting and to make sure that the appropriate adsorbents are used. This slide here shows some of the different adsorbents that are available. The ones at the top of the table have a low surface area. You can see 5 meters squared per gram, as opposed to the adsorbents at the bottom of the table that are 1,500 meters squared per gram. Those adsorbents at the bottom are much stronger and more tenacious. They'll hold on to very volatile compounds, letting you get back to the laboratory for analysis. But the adsorbents at the top, they'll allow you to target much heavier compounds and be able to desorb them off again, either by thermal absorption or solvent extraction when back at the laboratory. So it's important to work with your passive vendor to make sure that you're using the appropriate adsorbents to target the compounds that are of concern at your site. To install samplers, it's very straightforward. Using simple hand tools, we recommend using a hammer drill with small diameter drill bits, typically 1.5 inch diameter down to a 1/2 inch diameter, where you're creating holes as shallow as 1 foot down to 3 feet. And it can be used both in grass covered areas as well as through asphalt and concrete. For more detailed procedures, you can go to our website where you see full videos showing the installation procedures. I want to talk a little bit about the design considerations that you should keep in mind when you're developing your soil gas survey, particularly for passive soil gas surveys. We like to have our samplers out in uniform grids. That way you are less likely to have a bias and miscontamination, because contamination is typically not where you're going to expect it to be. There's always surprises out there. And often when there's not enough samples collected, we see hot spots on the edge of grids. So we really try to work with our clients to develop an appropriate grid pattern across the site that'll have good coverage and still stay within the budget. You can also use a more focused sampling pattern if you have just specific areas to investigate, like underground storage tanks, septic fields, known features where you really just want to focus to see if there's been releases there. When we're tracking contamination in groundwater, we put samplers out in transects, and we've tracked groundwater contamination at depths greater than 75 feet. With this approach, we recommend having the samplers in spacing of 25 to 100 foot between samples within the transect. And then transects typically are 100, 200 feet or further apart, depending on how large the plume is, so we can really focus in where the center of the plume, the contamination in the center of the plume. For identifying source areas, we recommend spacing of 15 to 30 foot to identify those source areas and make sure we're not missing contamination. But some sites are obviously too large for that tight of a grid pattern. The budget won't allow it. There we recommend stepping out to a larger grid, 50 foot or even larger, to make sure you still have coverage across the whole area, but then tightening up the grid in those areas of greater concern based on available site information or features that you see out in the field. When sampling for shallow groundwater contamination, you're going to need to use a tighter grid spacing because there's less distance for the gases to diffuse from the groundwater to the near surface. The main path that gases want to follow is vertically, all things being equal, based on gravity and pressure. But gases also will diffuse out diagonally and laterally to a lesser degree. So the less distance you have from the near surface down to the source, or where the contamination is present, the closer you're going to need to have the grid spacing. And utilities also to keep in mind, they can be to your advantage or work as a disadvantage for your survey. Because if you're looking for contamination, you put your samplers above known utility lines, they'll act as a sink for gases to accumulate in there and migrate along that utility line, and some of it will be diffusing upward where we'll be picking up with our passive sampler. But if you were to have a utility line going through your site that you didn't know about, you might have a measurement there that's an anomaly and think it's a hot spot when really you're just picking up contamination from a utility line that's transporting it from a remote location, someplace laterally distant. So I mentioned the samplers can be installed in typically holes to a 1 to 3 foot depth. They can be installed in holes that are extended to a greater depth by using direct push. We've advanced holes down to bedrock, and we've sleeved down to different depths to isolate where the contaminants are going to be measured. But ideally, you want to minimize the size hole that you've created, so that reduces the amount of time required for the gases to reach an equilibrium again with the concentration that's in the surrounding soil pore spaces. As far as an exposure period, when you're sampling, looking for source areas or identifying vapor intrusion, a pathway and risk, 7 days or less is fine. In fact, we've done surveys that only had the samples out for 24 hours. However, when you're tracking groundwater contamination or contamination at greater depth, you want to leave the samplers out longer. And by using a robust sampler that has a large absorptive capacity, you can leave them out for 14 days or longer, even leave them out for a month or longer, which we've done, to make sure that you have the sensitivity, and that you're also, while you're might be looking for source areas as one of the objectives, the other objective is to see if contamination is migrating off site. So you still want to be able to meet that objective of picking up contamination in the groundwater. And by leaving a sampler out for 14 plus days, you'll be able to meet both objectives. The actual sampling period is going to be dependent on the site conditions, the soil porosity, how tight the soils are, as well as the soil moisture, which will reduce the diffusion rate of gases, and the compounds of concern, how heavy they are, what's the molecular weight. These things you want to talk with your vendor and get their experience on how long the sample should be kept out. As Mort said, in soil gas, you can target a broad range of VOCs. We routinely are targeting fluorinated and petroleum hydrocarbons with method A260C. And we're looking also for TPH, looking for the lighter and heavier fraction that might be present out there to discern the age of the contamination and the type of contamination of its petroleum that's present. We also can target 1,4-dioxane, which is an emerging contaminant of concern. We routinely target this. It's in our scope of accreditation, and we have seen it at many sites with chlorinated contamination out there. It's a very water-soluble compound, but it still will show up in the vapor phase, particularly when the 1,4-dioxane is present in soil. Passive approach will let you expand the range of compounds you can target as opposed to active soil gas sampling, because the adsorbents will trap heavier compounds that you're not going to be able to get back out of a suma canister, or is not appropriate for Tedlar bags or glass vials or other sampling methods. So with a passive approach, you can target ACE and naphthalene, fluorine, heavier pHs, but also explosive compounds, pesticides, herbicides are targeted, alcohols and ketones can be targeted, as well as chemical warfare agents, which we've done on a few unique sites where our sampler have actually identified mustard nerve agent in soil vapor, which the analyses were performed by a government laboratory, and we understand that that was the only times that these compounds have been seen in soil vapor as opposed to air. All right, so passive soil gas samples can be analyzed with a variety of methods, using thermal absorption or solvent extraction to introduce the sample into the system. Beacon analyzes all of our passive soil gas samples using thermal absorption to achieve the greatest sensitivity and reproducibility, and uses GCMS instruments to provide the highest quality data. While a passive soil gas survey is used to screen sites, the data can be of excellent quality by using GCMS and including internal standards and surrogates with all the analyses. Because Beacon is DoD ELAP accredited for method A260C, quarterly limit of detection and quantitation demonstrations on each system are performed as our biannual proficiency tests for each compound on our scope of accreditation. So you're receiving data of a very high quality, although it's only screening results. And using gas chromatograph with a mass spectrometer with thermal absorption allows us to have a very low detection limit that can be reported at a high confidence. The demonstrated limit of detection for each compound in our method is 0.005 micrograms or 5 nanograms, with even lower method detection limits. Now, the data reported with a passive soil gas survey is in units of mass of individual compounds that are absorbed throughout the exposure period. Federal and state regulators are not accepting passive soil gas data converted to concentrations, but reporting the data in units of mass still meets the objectives of a passive soil gas survey, which is to collect high resolution data to effectively screen the site in order to focus where soil and groundwater samples should be collected, to identify whether a vapor intrusion risk might be present, tracking groundwater plumes, and focusing remediation efforts. That is to make sure that you are injecting or extracting those areas where your efforts would be most effective. The data being reported in concentration is not critical because we know that the soil gas concentration is going to change, but what is important is acquiring data that best reflects the variability in subsurface contamination and meets the objectives of the survey. With a passive soil gas technology, you want to make sure that there's as much uniformity as possible in both the sampler design and the analytical method, so you're able to achieve the goal of producing data that not only identifies hotspots, but also maps the lateral extent of contaminant plumes. All right, so switching gears, I want to go over a case study I finish up my talk with, where a passive soil gas survey was performed to identify hotspots as well as the lateral extent of tetrachloroethene and soil gas beneath a former dry cleaner and adjacent spaces. Beacon supported the environmental consultant with both the soil gas and the indoor air sampling for this project. This property is located in a retail mall in an urban area where a new tenant wanted to take over 2 units that housed a former family-run dry cleaner and a store. The red line shows the location of the former dry cleaner, which it, along with the former retail store, were vacant at the time of the investigation. The first step was taken by the consultant to collect indoor air samples within each of the 2 spaces that are separated by a block wall with ceiling heights about 12 feet. The results found that the indoor air concentration of PCE was 22 micrograms per cubic meter, which was above the acceptable level of 8. A quick screen was then performed by developing temporary vapor ports that were purged with 3 volumes of air and then sampled using colorimetric tubes appropriate to target PCE. Screening results of 1.5 and greater than 10 ppm of PCE indicated further characterization was required to identify the extent of contamination in order to assist with the design of an appropriate remediation approach. The consultant first wanted to sample the indoor air not only in the 2 spaces to be renovated, but also in the other adjoining spaces and hallways. Samples were collected over an 8-hour period in the breathing zone at approximately 1.5 meters above the floor using sorbent tubes and low-flow pumps following method TO17. The results found an exceedance in the former dry cleaner space near where the dry cleaning machine was previously located, as the first round of sampling had also indicated. But all other measurements were below the exceedance level of 8 micrograms per cubic meter. A PSG survey was then developed to assess the extent of contamination in soil gas beneath the former dry cleaner and the adjacent space to be taken over. A high resolution grid with 20 and 15-foot spacing between locations was employed. This slide shows the sampling configuration used at each location, where a 1.25 inch diameter hole was advanced to a 12-inch depth, and then a 1/2 inch diameter hole was extended to a depth of 3 feet. The upper 12 inches of each hole was sleeved with a metal pipe to isolate the depth at which soil gas is sampled. This is important because the more porous subgrade material beneath the concrete slab will act as a preferential pathway for lateral gas diffusion, and we have found that soil gas data better represents contamination in soil and groundwater when you prevent the sampler from sampling soil gas immediately within the subgrade material. So once again, here's a slide showing the PSG survey grid in relation to the indoor air samples. And I should note that it required 4 hours for a 2-person team to install the 38 samplers, and then following a 7-day exposure period, a 2-person team retrieved the samplers and patched the holes over a 2-hour period. Samples were then submitted to Beacon's lab and analyzed following method 8260C. And what we found was the hotspot was where it was expected, but the contamination was extending south in the direction of the expected groundwater flow as well. You'll see the locations north of the former dry cleaner reported lower measurements and non-detects, suggesting that the plume was not extending further beneath this large retail mall, but possibly was extending out beyond the outside wall south of the dry cleaner space. Following collection of the passive soil gas samplers, 3 temporary vapor ports were installed at locations down gradient from the suspected hotspot to additionally measure soil gas concentrations at 12-inch depth. The 3 locations sampled are shown in the red triangle. These samples were collected using sorbent tubes and low-flow pumps, and then were analyzed following method TO17. The results from both the passive and active soil gas samples are shown here in this table, and you will note the strong correlation between both data sets. As an additional exercise, because it was not necessary for the objectives of the survey, but we was interested to see results, Beacon analyzed the correlation between the passive soil gas and the active soil gas results at these 3 locations using a power function to best represent the relationship with the data that has an order of magnitude difference. The power function equation is shown in the graph, as is the correlation coefficient, which you can see was exceptional. The table below provides what the calculated concentration would be at each of these 3 locations by applying the power function equation to the passive measurements. As you can see, the relative percent difference between the measured and calculated concentrations is very good. Next, the power function equation was applied to all passive soil gas results to calculate the soil gas concentration for each location. This approach is what we refer to as the master concentration tie-in, and additional information on this can be found on our website. But these results were then mapped for comparison to the original passive soil gas data and to provide estimations of soil gas concentrations beneath the slab. So what we see here is that the data set provides an example of the spatial variability of soil gas concentrations that are routinely found, which highlights the challenge of collecting a single soil gas and indoor air sample to establish an attenuation factor. Based on the results of the soil gas survey, a subslab depressurization system with a fan was installed, as shown here, in those areas of highest concentrations, as determined by the passive soil gas survey, to effectively mitigate the soil gas and resulting indoor air concentrations. After the system operated for a week, indoor air samples were collected following method TO17 and analyzed. Results showed that the concentrations first measured in August had dropped to acceptable levels by October, and that the new tenant was able to start renovations to occupy the 2 units. So in conclusion, spatial variability of subsurface contamination is the norm, and that's what we've seen for over 20 years of doing thousands of soil gas surveys. And high resolution sampling strategies will significantly increase the probability of not only identifying the presence of contamination, but determining where the center of mass is located, so remediation efforts will be more effective. Passive soil gas methods, which collect time-integrated samples over days or weeks, are less likely to produce false negatives. And the passive soil gas technologies that have a good quality control in both the sampler design and the analytical method will produce data that best reflects subsurface contamination. And a passive soil gas survey can target a broad range of VOCs as well as SVOCs to locate organic contamination and guide your remediation strategy. So with that, I want to thank you again for attending our talk, and I invite you to submit questions through the portal. And Jordan, do we have any questions that were submitted this time?
We have a few. Actually, we can start off with ones for Mort. First question.
Am I unmuted?
Yeah, you are. You are.
Okay, good.
Yeah.
All right, I had several questions here. One asked,
Okay.
have we used this technique to look for 1,4-dioxane? And the answer is we haven't really looked for it. Depending upon your analytical method, when we've used the small glass vials, the 22 ml evacuated bottles, we're looking for, we can see 1,4-dioxane because we're using a straight gas chromatograph. But as you may know, the GCMS, because of its water removing, et cetera, procedures, is not very good for 1,4-dioxane. So when we're using larger containers, and we've done this, Suma canisters typically, we're usually getting a very poor reporting level for 1,4-dioxane, but we could potentially see it.
I can still see it actually here.
Am I still good, Jordan?
Yeah.
Okay.
We're actually going to.
Okay. Had another question here, radius of influence with a 6-liter canister. Somebody, I think in the Hawaii guidance, someone calculated how far you could see depending upon how much soil gas is going to go into a container. But I did a back of the envelope calculation just now. A 6-liter Suma canister, if you had 35% porosity in the sand, gravel underneath a slab, that would represent 0.6 of a cubic foot of a sample. So depending upon how thick your sand gravel is underneath a slab, you'd see several square feet. You'd have maybe a 1 or 2 foot radius, but not real big with even a 6-liter Suma canister. So a radius of influence, maybe a foot or 2, depending upon the thickness.
And Mort, this is Roger. I ran those numbers. Now I assumed a 20% porosity
and then a thickness,
Okay.
a fill material on the slab of 15 centimeters, and I come up with about a 25 centimeter radius of influence. Just for comparison, for
Okay.
a 100 liter soil gas sample, say sub-slab, that comes out to about a 100 centimeter radius of influence. And for the first person who can figure out how to get a 100 liter sub-slab soil gas sample, I'll buy them a beer at Duke's in Waikiki.
Does that include airfare?
If you pay for the, yeah, exactly.
I will send
All
a
right.
rowboat.
Sounds good. Okay, had another question. Does a large number of points increase the risk of vapor intrusion? I think what they meant by that is, do you have a risk of failing? You're not going to actually cause vapor intrusion, assuming you don't have a leaky point. And again, depending upon what you're using, I haven't had trouble with the vapor pins leaking. But I think what they were really asking is, does a large number of sample points increase your risk of exceeding your soil gas screening level? And the answer is yes, it does, because it's a whole lot easier to pass vapor intrusion screening levels if you never really find the problem. But unfortunately, you do want to see the problem. I should mention to that end, I submitted comments to the EPA guidance where I suggested that instead of using an attenuation factor of 0.1, you should be able to use something much more plausible like 0.01 or 0.001 if you collect 8 or more samples or something along that line. But yeah, you're more likely to find a problem, and that's good. I should mention, by the way, that we, most of the time when we do these screening things, it's not the exception, it's the rule that we find the real problem is not where people thought it was. So yeah, that will happen if you collect a lot of samples. There was another question on how long you can leave. I think it was the same questioner. How long can you leave the vapor pin in place? 4 or 5 years, whatever. I've left them in place typically for no more than a year because I'm doing that for vapor intrusion sampling. We usually need to sample 4 quarters. So we'll go back 4 times and then pull it and remove it. The brass vapor pins, I usually use brass if I'm doing one-time sampling, stainless if I'm doing, if I'm leaving it in place. Just of course, it's more corrosion resistant. But if I'm only doing a one-time event, of course, then we pull it out at the end. And I forgot to mention earlier on, but the vapor pin is reusable. You strip off the silicone sleeve, decontaminate it, and use it again. And I've used mine on average 7 or 8 times each. So the second time, they're virtually free. But I've left them in as long as a year. And someone asked this, I've left a few of them in place for several years. They asked, does the silicone sleeve wear out? Not that I know of, not in the samples I've seen. If you had a very high level VOC, hydrocarbons or something, maybe it might react, but they'd be very simple to pull out and replace and hammer back in, I suppose, if you had to, but I have not seen that. Finally, there was a question on cost of that study we did of the 144 plus points. The simpler thing, probably depending upon your rates, your billing rates, etc. We had our cost was 2 guys, 40 hours, 80 people hours, a hammer drill, and a PID or a multimeter, and the vapor pins themselves. Of course, vapor pins for me are cheap, but what you would pay for a vapor pin, we have the contractor kits that include the installation tool, etc. You only really you don't need all those things for 10 times. But the contractor kit has 10 vapor pins and those accessories. And then stainless, it's 850, brass is 750. Individual pins, if you want more, are $50 for stainless, $40 for brass. And again, they're reusable. So the first time out, it'll cost you a little more than stainless steel set in cement. But by the second time, at least you've broken even, and the third time they're virtually free. If you're interested in vapor pin, looking at them more and getting prices, they also have accessories, filters, etc. If you feel the need that attach to the underside of them, you can go to www.vaporpin.coxcolvin.com. So, and there was one other question about the radar plot. It is not published. I gave a presentation, I gave a webinar for MSECA, MSECA. I've given a couple of other presentations, and I'd be happy to send you a white paper. I'm planning on publishing it later this year. But if you contact me, if you email me through coxcolvin.com, and my name is Mort Schmidt, MORT_SCHMIDT at coxcolvin, one word, COXCOLVIN.com. I'll be happy to send you an article that describes that great art plot stuff. So thank you very much.
Yeah, thank you, Mort. And I'm going to turn things over to Harry now so he can go through some questions that he has. And yep.
Okay, thanks, Jordan. Yeah, there was a question on the range of being able to pick up contamination at what depths we can see contamination. That's going to be all dependent on the soil conditions and the compounds we're targeting. From experience, we've seen contamination in depths greater than 75 feet. Obviously, that's in soils that have a larger porosity, allow the gases to diffuse to those great distances. But we've had excellent correlation with follow-on wells that were installed by tracking a plume in the southwest United States, where we first set up transects to determine the extent of the plume, and then we came back with a line of samplers parallel to the groundwater flow to really zero in on the length of the plume. And it's going to also be dependent on the type of compounds that are being targeted. The chlorinated compounds, they will attenuate much less likely than the petroleums. And so they're recalcitrant, and they will make it all the way up to the surface, where the petroleum hydrocarbons, particularly BTEX, will attenuate when it gets into oxygen-rich environments. So there we tend to look for the aliphatic hydrocarbons and look at TPH more so than the aromatics. We're looking for petroleum contamination. But even still, with petroleums, we've seen contamination at considerable depths. Ideally, when looking at contamination down at 20 foot, we consider that not to be a challenge, unless it's very tight clays. But for sites that have greater depths to contamination, we can also set up pilot studies first to make sure that it works before we go ahead and install the samplers. We had another question about, can you have too many compounds being present? Does that cause a problem for the sampler? Well, the adsorbents that we use have a wide range of affinity for compounds, from very light vinyl chloride out to PAHs. And we've done surveys where we've seen well over 80 compounds present on the sampler from what's in our calibration, as well as what we have looked for as TICs, tentatively identified compounds, and at very large masses also. So we have seen our adsorbent samplers be able to adsorb a broad range of compounds, seeing PAHs at the same time vinyl chloride and other light compounds are showing up. Another question is on the effects of rain and moisture. Rain obviously can cause the pore spaces in the soil to be filled up, and the gases will not be able to diffuse through those pore spaces while they are saturated. However, you put the samplers out, you say they're in dry or just typical conditions, and then you have a rain event and the soil pore spaces fill up with water. Gases will not be moving then, but as the water subsides after the rain event ends, gases will then start moving again. And because we're using hydrophobic adsorbents, they will continue to absorb compounds even if they become wet. It's not necessary to have a membrane or plastic around them to protect them. We had some questions about reporting the data as a concentration, as we did with the mass deconcentration tie-in. That is a exercise that we can provide on a site-specific basis, where we have the measurements by passive soil gas as well as active soil gas, establish that correlation for the site, and then apply it to all the sample locations to derive what the concentrations were at each of the locations. That is data that can give you guidance still on the concentration. It's not concentration that's going to be accepted at this point by regulators as a definitive concentration. But keep in mind, the purpose of the passive survey is to screen the site, to determine where you have contamination, whether it be in soil, groundwater, or even soil gas. If a risk assessment concern from vapor intrusion is the objective of the survey, that is the follow-on investigation to be required to determine what is the concentration that's present there, and to sample at different periods to see what is the average and high concentrations that might be present. So it's a separate objective. but by reporting the data in units of mass as a passive soil gas survey does, still meets the objectives of determining where you have contamination in both soil and groundwater and where you want to focus your remediation. And there's a lot more information on our website. I know we're past the hour, as well as case studies. And you can contact me. You've seen my information there. Or call us directly at our office at 800-878-5510. And we'd be glad to evaluate your applications and share more about how passive soil gas technology is used to overcome the challenges from spatial variability in subsurface.
Okay, thanks, Harry.
Hey, Harry, this is Roger. I have one more question for you. Let's say I want to determine the mean concentration of a VOC within the middle 1/3 of a building slab. Can you install multiple passive samplers and then combine them in the analysis so I just get one analysis and just one number? I'm not really interested in the variability. I just want the mean.
We can. So
also.
Yeah, what you refer to is you have a decision unit there in your building and you want to determine what the mean is for that. What we would do is we would have a sampler at each of the location, and then when we get it back to the laboratory, we can set it up in our system to desorb each one of those traps onto a focusing trap and then analyze that focusing trap to give you the measurement from all locations with one analysis. So that can be done.
So that would allow me to put in a lot more passive samplers within my decision unit area to get better data quality.
That's right. And so you get more data density while still keeping your analytical costs down because it wouldn't require as many analyses.
Okay, great.
Okay, yeah, so once again, I want to thank our panelists, Mort Schmidt and Harry O'Neill. They good presentations from you guys, a lot of good information. And yeah, I also want to thank all our audience members. Just with the slide up right now, just want to mention that we have future webinars coming up. So we're still working on finalizing dates, and we have speakers we're trying to work through, but as you can see, we have some topics we're going to try to discuss this year. So if you have any questions, you can contact Roger. You have his email up on this slide, and everyone should have my email address from multiple emails from Zoom. So feel free to contact either of us with questions for the upcoming webinars or any of these topics. And yeah, feel free to reach out to Harry or Mort as well if you have any of these, any other questions. But I just want to say thanks to everyone, and yeah, we'll be in touch, and hope to hear from you all soon. Thank you.